Okay, I hope you can see a big white slide with a new title I prepared for this presentation. Sorry to switch up on you. I wanted to do something a bit more vague and a bit more cloud native. So I'm going to talk about cloud native secret management. I am Micrea Cosbuc, as Sam just introduced me. I'm a cloud native engineer with Container Solutions. This explains the first half of the title of this talk. And hopefully in the rest of the half an hour, 40 minutes, I will make it a bit more clear what the second part of it is. Now, because the title is so vague and broad, I'm going to have to narrow it down a little bit. So what we're focusing on is the following steps in the software development lifecycle: the source code, the configuration of the application, and the execution environment. I'm mostly not going to talk about the source code of the application itself, but the way it's managed. And with configuration, I will focus on the sensitive informations like credentials, certificates, etc. And when it comes to the execution environment, we're talking about Kubernetes. I wasn't sure about how familiar everybody is with Kubernetes, so just a quick refresher, so making sure we're all on the same page. I'll just cover the elevator pitch for Kubernetes. It just helps you take a cluster of machines for running container workloads, and it helps you efficiently manage it. We will need some basic concepts, pods and secrets. As you probably know, pods are the smallest deployable units you can create and manage in Kubernetes. Now, therefore, managing one or more containers, sharing storage and network resources. And the secrets are the basic abstraction used in Kubernetes for storing and managing sensitive information. We're also going to cover a bit controllers and operators, which is going to make the meaty part of this presentation. And before we get into that, let's quickly discuss the security properties of Kubernetes secrets. At the administrative level, secret data is stored in the etcd backend of Kubernetes. And because of that, encryption at rest is recommended for etcd. There's more there's more of a checklist you can go through for when you're putting your cluster on the internet, but this is a bit outside of the scope of this talk. There's a really nice checklist called "Help My Clusters on the Internet," based on a KubeCon talk from 2020. This is maybe where you want to go when you're securing your Kubernetes cluster in the first place. Now, for the purpose of this presentation, it's important to note that when you define a secret as a Kubernetes manifest, this secret contains the secret data encoded as base 64. This means that sharing these manifests is insecure. And when we're thinking about sharing and collaboration, we get to the next part of the context of our problem, how we deploy our software. A classical model of deployment has us store our source code and non-confidential manifests in one or more repositories in source control, and delegate the responsibility of injecting sensitive data to CI/CD tooling like Circle CI, Travis, Jenkins, etc. This is where you just inject secrets before it ends up in your Kubernetes cluster. While this achieves some separation of concerns, it adds an extra potential point of failure in the CI/CD tool, which must be treated with the same security constraints as the Kubernetes cluster where we plan to run our workload. Beyond that, not having some representation of the sensitive data in source control makes it difficult to manage the deployment of one software package in multiple environments. You might end up with the known complaint, "It works on my machine," and then spend days figuring out what's wrong in the setup in your CI/CD. Ideally, what we want to achieve is a GitOps deployment where we store all the information we need to run in source control. What we were missing in the previous picture was storing the secrets together with our code and deployment manifests. However, we just reviewed that secret manifests are not safe for sharing, as their format has the security equivalent of storing them in plain text. To solve this, first we'll take a look at solutions which use an encrypted representation of the secret. We will take a closer look at Helm secrets, at sealed secrets, but we could just as well look at Helm secrets or Camus. All these tools approach the problem in a similar way. The sensitive data is encrypted, producing a safe recipe for the secret to store in source control. So Sealed Secret is a project out of Bitnami Lab. It's probably the first approach you're going to find if you're researching how to do secure storing of secrets in a GitOps environment. And yeah, as I mentioned, it works with encrypted recipes for the secrets. Before watching it in action, I'm going to do a quick demo with Sealed Secrets. Let's revisit the deployment picture if we were to add Sealed Secrets in the mix. First of all, you can see our original secret outside of source control. This gets encrypted by kubectl, a client-side utility, into a sealed secret, which can be safely stored in our repository. From there, it can be applied to the target Kubernetes cluster. Just a quick side note, in the GitOps flow, I replaced CI/CD tooling to illustrate the simplicity of what should be possible with the information available in the repository. In the real world, you will not do kubectl apply, but you'll probably use something more sophisticated. Once our manifests are applied to the cluster, our secret recipe, the sealed secret, is picked up by the sealed secrets controller, decrypted, and applied as a regular secret. It can now be picked up by the pods where our application is running. You might be wondering now, what is a controller? How can it decrypt the sealed secret? And what is the encryption mechanism used by kubectl? And I hope I can answer this with a quick demo. First of all, I hope my screen is visible. I'm going to assume it is.
It is.
I have here a Kubernetes cluster where I'm running the sealed secrets controller in the kube system namespace. Have the sealed secrets controller. I will create a secret on my local machine and then seal it with kubectl. So I'm just creating a generic secret with a fake client ID and client secret for GitHub. And to seal it, I'll just input the secret to kubectl and it will output a sealed secret. If we look at sealed secret, we can see we're getting a different string for client ID and client secret. Now, I'm going to apply the sealed secret to my cluster. I'm going to create a new namespace. So applying the sealed secret to the cluster gives me the opportunity to talk about what the controller is in general and what the sealed secrets controller does in particular. So controls are simply control groups that watch the state of the cluster and make changes when needed. The sealed secrets control in particular watches the cluster for sealed secret resources, like the one I just created, and synchronizes them to simple secrets. So when I apply this manifests, I should have a Kubernetes secret created in this namespace. Of course, I applied it to the default namespace. Okay, this is because of my kubectl create secret. Okay, the magic of demos. Let's create it again. Okay. Sealed secret namespace. Okay. Now I should be able to see the secret. Yes. And if I get the secret, I should see the same client ID and client secret I used to create the secret, which well, okay, encrypted in base 64. Now, sealed secret uses asymmetric encryption, but we didn't see any keys in the kubeseal commands I ran. This is because I'm connected to the Kubernetes cluster, and kubeseal was able to retrieve the public key at runtime. So when you're applying sealed secrets to a cluster, it's very likely that in your CD pipelines you don't have access to the Kubernetes cluster. What can you do in that case? So one thing you can do is get the signing key ahead of time from the deployment of the sealed secrets controller. Okay, I think we have plenty of logs, so we don't see the key. But with the computer connected to the cluster, you can do kubeseal fetch cert, and then whenever you're sealing a secret with kubeseal, you can pass this certificate as a parameter to your kubeseal command. And this way you can seal your secrets without having a connection to the Kubernetes cluster. Now, getting back to the slides. So you can see it's a straightforward application of asymmetric encryption, and this already gives us one solution for secret management. There's a bit more to sealed secrets, like scopes, but I will keep it out of this talk, and we can talk about it. We can talk about these features later. Now, it seems like storing the encrypted representation of a secret is a good enough solution, and it begs the question, why would you do something different? Now, a good argument for me is, while the security primitives for this approach are strong, where this is likely to fail is in implementing it as a policy in the software development's lifecycle. If the developer has access to the secret and needs to encrypt it before committing it to source control, how are we going to enforce not using those credentials from somewhere other than the target environment? And on the flip side, if the developer doesn't have access to the original credentials, there's an overhead to getting the sealed secret in version control. You might need to get somebody else to seal it for you, and then you need to worry about passing the secret around. This is where a simpler approach comes in. Instead of working with an encrypted version of the secret, we can work with a reference to sensitive data stored in an external system like Vault, AWS Secret Manager, etc. This is exactly the approach taken by the external secrets operator. What happens here is that a secret recipe can be stored in version control, and once applied to the cluster, the external secrets operator picks it up, connects to the remote system, be it Vault, AWS Secrets Manager, Google Secrets Manager, retrieves the sensitive data, and syncs it to a secret in the cluster. It's a very simple idea, but depending on the implementation, it can provide some real benefits. Quick history of the project. It started with the client in container solutions running multiple services across multiple environments. AWS Secrets Manager was the preferred way to manage secrets, and the setup was not fully automated. This created problems with getting the right credentials for the right environment. Sorry about that, my mouth got really, really dry. Now, a combination of tens of environments with tens of services leads to hundreds of credentials, which is nothing crazy in most production systems. But when you want to provide fine-grained access to those secrets, while also implementing GitOps, it can become a huge headache. The way the external secrets operator solved this initially was by this architecture. The important choice made was to have one operator per external secret provider. This might mean a different operator for AWS and a different one for Vault, but it can also mean a different operator per environment if your secret stores are segregated per environment. So you have, if you're writing application development, you can only access secrets from the development operator. This has the interesting property that because the operator is the only owner of the information required to connect to the external store, applications might be able to access the credentials required to run, but they will not be able to access any other credentials from the secret store. I'll give you a quick demo of working with this operator, but before that, I have to bring the story from history to today. The project was stable and used in production for a long time with this initial architecture. However, recently there's been a breath of life given to the project and other similar projects by a discussion on one of the more popular options repository, one from GoDaddy. We quickly realized that there's many groups solving the same problem with a very similar implementation, but slightly different. This has led to an effort to synchronize all these efforts around the custom resources these operators manage. This has led us to a change in architecture where the external secrets operator watches more. Not only watches external secrets, but also watches secret stores, which are now the representation of the external secret management systems. This means that now a single operator can connect to multiple sources. However, this complicates permission management when you want to preserve the property the old, simpler architecture had. Let's jump into a demo and see how it works out. So for this demo, on the same cluster, I also have the external secrets operator installed. And I didn't mention it yet, but the difference between an operator and a controller is that an operator embodies the knowledge of a single domain, in this case, external secrets and secret stores. It observes custom resources under its own API extension. So we would have something like this, external secrets under the external secret operator containersolutions.com extension. All right, let's go through the demo. What I have here is a secret store of type AWS Secrets Manager, which I will be using to get secrets from, and an external secret which references this secret store, and it looks for the calendar key and the version latest. If I apply this, in a quick while, I should also have the equivalent secret here. Okay, sorry about this. I upgraded my version of KNS and Minikube, and apparently I'm applying them to the default namespace. Or not. Let's first make sure, okay, I have the secret store. I have the external secret, and I should also have the secret. Okay, this will probably kill my demo, but let's just, for our curiosity, look at the logs of the external secret operator. Okay, I think I'm on a development version and I'm not pulling the image properly. Okay, I'm sorry about that. I'll go back to the slides. You will have to believe me that this creates a secret in the Kubernetes cluster based on that AWS Secrets Manager reference. Okay. Now, what's sensitive about this current implementation is that access to the external secret stores has to be restricted to the operators. And secret stores should not reside in the same namespace as the applications are running it to avoid leaking unintended credentials. This is just one of the issues we've encountered with the new approach. And we're looking for contributions to help us address some of these issues. You're welcome to check out our list of issues on GitHub. There's also an extensive contributing guide you can go through. Right now, we're mostly focusing on packaging and documentation improvements and adding new backends, because those are easy to port. Because what we're doing right now, as I mentioned before, we're looking to unify all these external secrets efforts. We are gathering all these under a single repository in a new organization, external secrets, and we're working here on creating a new project based on the efforts of of our operator under container solutions and the efforts on the more popular operator from GoDaddy. So you're also welcome to try and help out with that. What's next for the project is maybe having it as a CNCF incubated project, and we have a pretty active community under the Kubernetes Slack and external secrets, and I'm looking forward to seeing you there, and hopefully we can collaborate on extending this external secrets operator. I have a couple of references here, which you can follow once I share these slides with you. I'll probably share them in the Software Circus Slack channel, which I have yet to join.
There is a way to bind credentials of, for example, Google Compute Engine, or at AWS you have the similar thing, Irsa, to bind credentials of those platforms to service accounts of pods. If the external service controller would be getting its own service account, it would be able to access those stores without any credentials. So,
yep.
so okay. Did you consider that?
We haven't. So this solution came from the idea of unifying all the CRDs from all these operators, and we had the discussion of adding a specific secret store CRD. But this indeed, if we know we have a cloud managed solution for storing secrets, it definitely seems like a use case where you don't want to use the external. Yeah, you don't want to use an operator if you can integrate as easily with a cloud provider. So our solution also covers a setup where you're connecting to some other service with its own credential system. But indeed, for a cloud provider, if you can do it as easy as that, yeah, probably an operator like the external secrets operator is overkill.